Welcome to the next chapter of differential equations. Whatever the numbering of your book is, we are going to be in Laplace transforms now for a few weeks. And it's huge. It's like going to another planet. It is so weird. This Laplace guy, who's been dead a long time, had this brilliant idea that we're going to take a look at. And it drives the whole chapter, this brilliant old idea. But it's like, honestly, it's like going to a place where everything is wildly complicated and different. But after you understand it, it's not so bad. So here's the stuff. Here's what we're going to be learning. Here's the notation. It's this cursive L bracket y of t. And this L is an operator. It takes a function and gives us another function, uppercase y. And it's a function of s. So it actually changes the variable on you. Here's the definition of it. This is Laplace's idea. You take the integral from 0 to infinity of your original y of t, whatever this function was. You multiply it by e to the negative s of t. E to the negative st, not s of t, e to the negative st, dt. So you do this integral. Usually it's an integration by parts. But anyway, you do this integral. And you notice you have to take that the limits of integration. Whatever survives, remember t is going to be replaced by these limits of integration. So t is gone. Your answer is going to be in terms of s. Now here's what you have to be able to do. You have to be able to use a table. It's the very last page of this chapter. So get a bookmarker. Mark this thing so you can always go to it. That's what we'll be doing in chapter 6 or chapter 5, whatever it is in your book. Laplace transforms. God, just trying to scare you. But this is what it's like. I've copied 2 of the formulas down. The Laplace transform of e to the at is 1 over s minus a. Another way to read this is the inverse Laplace transform of 1 over s minus a is e to the at. So the book tried to indicate that you can read this table 2 ways by writing the bracket L, the L bracket y, and the L inverse bracket y at the top of the table. It's kind of confusing until you realize they want you to be able to use the table for both. All right, I'm scaring myself looking at this. It's just me. We're still on Earth, but we're doing this really wild math. Wait until you see what we can do. It's really quite exciting. Anyway, so let's try this one. The Laplace transform of t to the n. So that'd be t to the second or t to the 1/2 if you had square root. T to the n is going to be, the Laplace transform is n factorial. Now you don't have a factorial for 1/2, so let's do just integers. N factorial over s to the n plus 1. So I'm just going to do this with you. One time, the book does 2 examples. Unfortunately, both of them are exponential, which is the easiest one. So the book does a few examples. I'd like to do a polynomial. The bracket, the Laplace transform of L, so it's L bracket t squared. The Laplace transform of t squared is the integral 0 to infinity of t squared e to the negative st. That's the definition. Now, I did the tabular integration by parts. Remember when you have t squared e to the negative 5t or e to the negative 10t or whatever? You can do the tabular integration by parts. Well, s is not the variable here. T is the variable. S is just some letter. So I did the tabular, and I'm going to be evaluating from 0 to infinity. And a funny thing happens. Check it out. Check it out. Check it out. Be with me on this one. Here we go. I got the right implement. Ha 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 ha. We're going to see which things go to 0 here. A lot of things die. So, like, look at this thing. I'm putting in I'm putting in infinity for t. So you have the t squared over e to the st. T goes to infinity. Who's bigger, t squared or e to the st? Now, s can be 7. It could be 2.3. Whatever it is, this guy here, t's going to infinity. S has to be positive. So this downstairs grows bigger than the upstairs. So when you put in infinity, this thing is 0. And then you put in 0 for t. This thing is 0. Same thing happens here. You put in infinity for t. This e to the negative st wins. So that's a 0. You put in 0 for t. This 0 turns the whole thing into 0. One piece doesn't go to 0. It's the very last part of this integration by parts. The very last part doesn't have a factor of t. So the infinity for t still gives me a 0. If you look at that far end there, but I have a negative. So it's negative of 0 minus 2 over s cubed because I put in 0 for t and e to the 0 is 1. So the whole thing boils down to be just 2 over s cubed when you do the subtraction from the definite integral. And if you notice the formula, if this n was 2, I'd have 2 factorial, which is 2 divided by s to the third, which is what we got. So nobody does these things by hand. They just read them off of a table. We never are going to be doing what just happened. But it's doable, and people have done them for a long time. I will never ask you to do one of these things by hand. However, we will go back to the definition once in a while, and here's a classic example of going back to the definition to do something interesting. The X out of the way. So isn't this wild? We can do the Laplace transform of dy dt. We don't even know what y is, but we can do the Laplace transform of dy dt. So the book does this one step by step. It's another integration by parts. I'll never ask you to do this all the way out, but we use this idea like crazy because we can do the Laplace transform of dy dt, and it comes out to be negative y of 0. Remember putting in the limits of integration. Well, y of 0, that's initial condition, usually given. So that means that we are going to be doing differential equations with differential conditions all the time. And then it's s times the L bracket y. So if I want the Laplace transform of y prime, it's negative initial condition plus s times the L of y. So what's the point of that? Well, there's several big points. We'll see in a minute. But here's what's going on. This L is an operator. L is a linear operator. Let's take a look at what it takes to be a linear operator. A linear operator, taking its name from linear algebra, a linear function, a linear operator has to distribute. So L of f plus g, L of bracket f plus g is the same as L of bracket f plus L of bracket g because L is an integral. Can you integrate term by term? Always. So I can integrate term by term, so that means this line is cool. And how many times have you moved that constant out front? You have a constant that's bugging you. You move it out front of the integral. Sure, we do that all the time. These two properties together are what makes a linear operator. And we've already known 3 other linear operators in our life. The derivative. Because can the derivative be taken term by term? Yeah. If you have a constant times a function, is the derivative of it the constant times the derivative of the function? Yeah. Derivative works like that. The integral works like that. Can we just integrate term by term? Sure. Can you move the constant out front? Sure. And limits work like that. Limit takes a function, gives you a function. Let's take a limit and everything goes to a number. You know, there's still a function. A number can technically be a function. But the big idea is this guy, this cursive L, the Laplace transform, joins a very small menu of the biggest, most powerful items we've used, these operators. Have we not used derivatives, integrals, and limits like crazy in all your math major life? Now there's another player on the field, the Laplace transform, and it's huge. Let's see how we actually use the Laplace transform. We just use the table, but we're going to use it to solve a differential equation, and this is your homework for next week. You got to go to the first section of the Laplace transform chapter and do some Laplace transform solving. So for next, do first Laplace section problems. Do some. You got to do your own problems. You got to get used to this. This is what we're doing. So I'm going to do one with you right now. Here's what our homework is going to be like. Here's what the kind of things we're going to be doing for the rest of the way it goes. Here it goes. Ready? So our differential equation that I'm choosing, I took it right out of the book. I have dy dt plus 5y equals e to the negative t. And I have an initial condition y of 0 equals 2. I'm going to need that if I do the Laplace transform of the derivative, which I'm going to do. So here's how we math people say this. Honest to God, okay? I went to grad school. I got a doctorate. They say, hit it with the Laplace transform. Now, the notation would be to say, I'm doing L bracket dy dt plus 5y equals L bracket e to the negative t. But nobody writes that down because we just go term by term. It's a property of the Laplace transform. So L bracket is -2 plus S, my fault, S L bracket y. That's from the thing that was down here. Plus, now we use another property of the Laplace transform. What's the Laplace transform of 5y? Well, it's 5 times the Laplace transform of y. This is equal to, now I'm going to do the Laplace transform of e to the negative t. I actually have a function of t. And according to my table, a is -1, so this is 1 over s minus -1. That's 1 over s plus 1. Now, if you write your s's like your 5s, you're in trouble. So you got to keep them straight, because I already have a 5 and a couple of s's in the problem. Now it turns into an algebra problem. We're going to solve for L bracket y. So add the 2 to the other side. I'm going to do the eraser method to save a line. This typically happens. Do not get a common denominator. Do not get a common denominator. Just leave them term by term. Now, I'm going to factor out L bracket y, and leaves me with s plus 5. That's still equal to 1 over s plus 1 plus 2. Now I can divide by s plus 5. My L bracket y is equal to 1 over s plus 1 times s plus 5 plus 2 over s plus 5. Can you dig it? Can you dig it? Isn't it cool? Isn't it cool? What's cool about this? Well, I now have y. It's not quite by itself. But if I could undo the Laplace transform, I'd know what y is. I'd have y equals. And apparently, undoing the Laplace transform is a thing. You know, you just got to do is read the table backwards. However, the table doesn't have factors down there. So here's what we got to do. We got to do partial fractions. I'm going to erase up here and do the partial fractions up there. So the book does just a few examples like this. And I'm only doing this one because I want to keep this video short. But doing the partial fractions, that's where you set up 1 over s plus 1 times s plus 5 equals a over s plus 1 plus b over s plus 5. This is a Calc 2 idea. I'm going to skip right to the chase. You multiply through by the common denominator, and then you solve, and you get, it turns out a is 1/4, and b is -1/4. So when I put those in here, I get a new structure for this. I get the following. I get a, let me get this down now. I get 1/4 of 1 over s plus 1, and I get -1/4 of 1 over s plus 5 plus 2 over s plus 5. So these two combined, that's 8/4 minus 1/4. I'm going to make this plus 7/4. I know I'm doing it fast, but I'm trying to keep this video quick. But it often happens that you get like terms. It's not unusual. Now I can hit this with the inverse Laplace transform. Y equals 1/4. Wait a second. A linear transform inverse is still linear. So the 1/4 just sticks around out front. 1/4 inverse transform of 1 over s plus 1, that's e to the negative t plus 7/4. Now I got to do that one, that's e to the negative 5t. And we are done, ladies and gentlemen. That's actually the answer. And you can check it in the differential equation. I'll leave that to you, but the check's beautiful. So what happens is, this certainly satisfies the initial conditions. When t is 0, I have 1/4 plus 7/4, that's 8/4, otherwise known as 2. Initial condition satisfied. Take one derivative of this, pop it into the differential equation with this, and 1e to the negative t lives. You do that. And that's what you can do on any of these problems. Now, you're supposed to say to me, McDaniel, I could have solved this problem. This is a chapter 1 problem. This is an easy problem. Well, this is not chapter 1, chapter 2, because it's not homogeneous. But it's an easy problem. How come we're doing linear? How are we doing Laplace transforms? Because it's how we learn Laplace transforms. We will be tackling some differential equations that we can't do any other way except with Laplace transforms. But you got to learn how to do Laplace transforms first. So please, go to your Laplace transforms chapter, do some problems from the first section, okay? That way the next time I do a video, I'm gonna do it as if you did some Laplace transforms. I expect you guys to do some work, because what else are you doing? Watching Netflix? Do some math.